Alright, didn't mean to do that. Let's try this again. Here we go. Factors affecting reaction rate. There are a lot of things that can affect reaction rate. So I'm going to scroll through this and go through them all. Alright, first of all, the nature of the reactant. Basically, what you have reacting. At the very beginning, we talk about baking soda and vinegar. You put them together, they'll react pretty quickly in a classroom. Alright? The breakdown of fossils to make fossil fuels takes millions and millions of years. Okay, so that's a very, very slow reaction. Okay? Formation of rust outside of like your bike could be a slow reaction. Alright? When you place hydrogen and oxygen, if you have some energy into it, it's a very quick reaction. Alright, so depending on what you have as your reaction, reactants, will depend on how quickly it goes. Alright? Some substances react more readily than others. Alkali metals. Uh-oh, we're going back to first semester here. Remember, alkali metals are the most reactive metals on the periodic table? Sodium, potassium. Those are the ones that have that one valence electron. You throw it in the water, blows up. Alright, so those are very quick. Alright, and this is just saying what I just said. You got your calcium and sodium. Sodium actually will react faster than calcium, because sodium has that one valence electron and calcium has two. Alright, but once again, what determines how quickly something will react? Well, what it's made of is one reason. Alright, the next thing we can look at is concentration. Alright, reactions speed up when you have a higher concentration of particles. Okay? If you increase the number of particles, you'll increase the number, or the reaction rate. Why is this? Well, think of it like this, alright? If you have a whole bunch of bumper cars, alright? If you're doing bumper cars and you have a whole bunch of them out there, if you have a lot out there, you're more likely to collide. You only have 2 or 3 out there, you can kind of avoid them and miss each other. Less collisions. And what do we say one of the things for a reaction to occur has to happen? Collisions. Okay? So, if I have more particles, I'll increase the number of collisions. Increase the number of collisions, you'll increase your reaction rate. Surface area. Alright, when the surface area increases, you also increase reaction rate. Okay? Sometimes baking soda actually can get a little moisture and get like a big old chunk of it. Alright? And so if I have a cup of vinegar and throw a chunk of baking soda in there, the only place where the reaction can occur between the baking soda and vinegar is on the outside of the baking soda. However, if I crush it up and spread it all out, now the vinegar and baking soda have more, here's this word again, collisions. You increase surface area, you'll increase the number of collisions. If you increase the collisions, you'll increase your reaction rate. So, increased surface area allows for more particles to collide. There it is. Thus increasing the reaction rate. Alright, temperature. Well, usually if you increase temperature, you increase reaction rate. Why is that? Well, let's go back to our definition of temperature. Temperature is a measure of average kinetic energy. Kinetic energy is energy in motion. So if I increase temperature, I'm increasing how fast the particles are going. And if I increase the speed of the particles, guess what's going to happen? More, you got it, collisions. More collisions will happen. So, this occurs because if the temperature is increased, the particles move more quickly, thus more collisions. Now you're starting to see a theme here. Alright? Collisions really control, or one of the main factors that controls whether reactions will speed up. Alright? Also, if the temperature is increased, you have more energy inside of there. And what do we say about activation energy? I've got enough energy for the activation energy to have enough for the reaction to go forward. Okay? So if I increase the temperature, I'm increasing the amount of energy in there. And activation energy is one of the things for a reaction to occur. Alright. Next thing. Add a catalyst. Alright. A catalyst is a substance that can increase a chemical reaction, alright, increase the rate of it, without being consumed itself. Alright? What this means is, if I add it in there, okay, so if I have a reaction, right, we've talked about this in class before, hydrogen peroxide. And I've told you, hydrogen peroxide, actually, if you leave it out for a while, will actually break down into oxygen gas and water. Right? Now, how do I make this speed up? Because this process takes a little while. Right? Well, there's this stuff called manganese dioxide, this black substance. Right? We actually used it when we did the hydrogen-oxygen rockets. Right? When you were making your oxygen gas, and that gave you this little bit of substance that had a black color to it. Right? That was manganese dioxide. Now, what does that do? It speeds up. It makes the breaking down of hydrogen peroxide to make oxygen gas go really, really fast. How does it do that? Well, what it does is, it's a catalyst. It lowers the activation energy. Okay? Catalysts lower the activation energy. So you don't need as much energy to make this reaction go forward. So what does that do? It actually speeds up the reaction if you do that. And there's a term, hopefully you remember from biology, it's called an enzyme. An enzyme is a biological catalyst. Right? We have lots of enzymes in our body. If you want to try a fun experiment, here's what you can do. Right? You want to see how a catalyst works? Take a cracker, okay? Cracker's salty. Chew it up, but keep it in your mouth. Do not swallow it. If you can keep it there for about 5-10 minutes or so, right, an enzyme in your mouth will actually start breaking down the starch that's inside of the cracker, right, which is just a long chain of sugars, into individual sugars. You'll break it down, right? And then what will start to happen with your cracker as it starts to break down and cause this reaction to speed up, right, is the cracker will actually start to taste sweet. So you can try this at home. Take a cracker, put it in your mouth, chew it up, right? Just hold it there and wait till you start tasting that sweetness in your mouth. That's the enzyme that's in your mouth, and I believe it's called an amylase. Right? The enzyme in your mouth that's actually breaking down the cracker into sugar. Alright. I told you that a catalyst will speed up a reaction by lowering the activation energy. So what we have here, and now this is a little blurry on here for even me, so I'll draw some of these things, is we have reactants. So here's our reactants right here. Alright? And this red line here, and I'll grab a red pen to do this. This red line here is how much energy it normally takes for this reaction to occur. Okay? So this red line is the amount of energy it takes for this reaction to occur. So here's your energy in, here's your energy out. Right? Quick little quiz here. This is the amount of energy in, more energy out. What type of reaction is it? Alright, if you said, what did you say? Say it louder. Alright, if you said exothermic, you're right, right? More energy out than in. So this is exothermic. So, in a normal reaction for whatever this is, it doesn't really say what it is, that's okay. This is how much activation energy you need. Alright? So this much. Now, we add a catalyst to the reaction. The catalyst is in green here. So if I add catalyst to the reaction, oh wow, look what happens. This is how much activation energy it needs. It needs a whole lot less energy to make this reaction go. So, add a catalyst, speed up the reaction. The cool thing, once again, about a catalyst is it doesn't get used up, meaning the reaction happens. Alright, I take out all my product, and guess what? All of my catalyst is still left. I can keep doing it. And keep doing it. Doesn't run out. Okay? So, that's a catalyst. Oops. Went too far. Now, a catalyst speeds up reactions. There's also something called an inhibitor. And inhibitors will slow down a reaction and sometimes stop a reaction. Now, why would you want to slow down or stop a reaction? Well, there's many reasons, but one way we use it is actually in the food industry. Right? What they'll do is they'll add inhibitors, a chemical, to your food to make it last longer and not spoil. Alright? So inhibitors are actually really good for the food industry. And I'm going to show you one. So I'm going to plop this up here. I hope you can see the difference in these. Okay? Now you got two apples. This is looking like a nice, fresh, cut open apple, and this is looking like a really gross, I don't want to eat it apple. Alright? Well, guess what? These apples were cut into at the same time. This apple right here does not have an inhibitor with it. So, the browning of this apple happens really, really quickly. Right? If you've ever bitten into an apple before, right, they'll brown, but they take a while. Why? Because your apples are like this one. They add an inhibitor to it. All right? And this inhibitor, what it will do is it will stop the browning of an apple. Now, taste-wise, that apple and that apple, they actually taste the same. Right? What happens is I think it takes away some of the crunchiness. If you're like me, I like crunchy apples. Right? And what it does is no one really looks at this and say, oh, that's appetizing, I want to eat this nasty brown apple. All right? Taste-wise, they're really similar, but the food industry knows we like to make it needs to look good for us to eat it. So we'll put inhibitors in this apple, make the apple last longer. We'll slow down the reaction. But you'll notice it doesn't stop the reaction, okay? Take a bite of an apple that you buy at the store, leave it out, come back to it. You'll see it does brown eventually, but it does slow down the reaction. So that's an inhibitor. Well, that's all I've got for reaction rates right now. So I hope you watched the video, and thanks for watching.